Today we shall be studying the topic on quantum efficiency and LED power of an optical source LED. The minority charge carriers created in a semiconductor source is directly proportional to the carrier injection at the device contact. If the carrier injection stops, then all the minority carriers return to equilibrium. The excess minority charge carriers or the excess carrier density delays exponentially with respect to time and is expressed as n is equal to n naught e raised to minus t by t, where n naught is the initial injected excess electron density and t is the carrier lifetime. When there is a constant current flow into an LED, an equilibrium condition is established. That is, the excess density of electrons n and holes p is equal. Since the injected carrier are created and recombined in pairs such that charge neutrality is maintained within the device. The total rate at which carriers are generated is the sum of externally supplied and thermally generated rates. The externally supplied rate is given by J by QD, where J is the current density in amperes per centimeter square and Q is the electron charge, D is the thickness of the recombination region. The thermal generation rate is given by N by T, hence the rate equation for carrier recombination in an LED can be written as dN by dt is equal to J by Qd minus N by T. The equilibrium condition is found by setting the above equation equal to 0, yielding N is equal to Jt by Qd. The internal quantum efficiency in the active region is the fraction of electron-hole pair that recombine radiatively, that is generating the photons. If the radiative recombination rate is RR and non-radiative recombination rate is given by RNR, then the internal quantum efficiency eta int is the ratio of radiative recombination rate to the total recombination rate given by eta int is equal to RR by RR plus RNR. As the excess carriers decay exponentially, then the radiative recombination lifetime is given by TR is equal to N by RR. Similarly, non-radiative recombination lifetime is given by TNR is equal to N by RNR. Substituting equation number 3 and 4. Equation number 1 was dN by dt is equal to J by Qd minus N by T, that is equation number 1, it is denoted as equation number 1. Equation number 2 is eta int is equal to RR by RR plus RNR. Equation number 3, that is the radiative recombination lifetime TR is equal to N by RR. Non-radiative recombination lifetime, that is denoted by equation number 4, that is TNR is equal to N by RNR. So substituting equation number 3 and 4 in equation number 2, eta INT is equal to N by TR divided by N by TR plus N by TNR. Now taking the LCM in the denominator and then rearranging it, it will be eta INT is equal to TNR by TNR plus TR. Eta NIT can also be rearranged as 1 by 1 plus TR by TNR. And if the bulk recombination lifetime T is given by 1 by T is equal to 1 by TR plus 1 by TNR, then the internal quantum efficiency is given by eta INT is equal to T by TR. The TR and TNR are comparable for direct band gap semiconductors, and also R and RNR are similar in magnitude for LED having double hetero structure junction. Next, in order to derive power input to LED, let us consider current injected into the LED, that is I. Then the total recombination in the active region per second is given by RR plus RNR is equal to I by Q. So this is denoted as equation number 7. Substituting equation 7 into yields, eta INT is equal to R by I by Q, that is equal to Q RR by I, or RR is equal to eta INT into I by Q. Optical power generated internally in LED is given by PINT is equal to RR H into V. PINT is equal to, substituting for RR from this equation, NINT I by Q is equal to into HV. PINT is equal to NINT I by Q into H into C by lambda. As V is a frequency is given by C by lambda. So we can say PINT is equal to the internal quantum efficiency into HCI by Q by lambda. Note that all internally generated photon will be available from output as output of device. The external quantum efficiency is defined as ratio of photons emitted from LED to the number of photons generated internally, and is given by eta ext is equal to 1 by n into 1 over n into n plus 1 to the whole square. The optical power output emitted from LED is given by P is equal to eta ext into PINT. So that will equate the optical output power emitted from LED. P is equal to 1 by n into n plus 1 to the whole square into PINT.